So let's get a little bit more technical and talk about systems as such. How does all this work? You effectively have something which is fairly imaginatively called an air handling unit. And so outside air is drawn into the air handling unit by the fan through a bank of filters. It's blown through a set of coils, which are not unlike the radiator in a car. The air is either heated or it's cooled, and the air is blown into the room. The air picks up the particulates and the contaminants, it picks up the heat, it goes out of the room, and it's largely recycled. By and large, air conditioning systems, the majority of air in air conditioning systems is recycled, but it's mixed with outside air so that you always have a certain percentage of fresh air in the process. So recognise that that's a very much let's call it a room. So how does all this happen? How does the coil get hot or cold? From a heating perspective, you've got a coil which has got hot water running through it. That hot water is heated by a boiler. You've got a closed circuit piping system, and that boiler, of course, is powered by gas these days. So what you have is the coil has got hot water running through it, the air is flowing through the coil, and it's warming up accordingly. On the cooling side of things, you have a thing the industry calls a chiller. A chiller is effectively a large refrigeration machine which produces cold water at around 4 degrees Celsius, and that water is circulated up into the coils. It takes up the heat from the air that's flowing through it and goes back into the chiller as such, and that's how the air is either heated or cooled in this box, which is called an air handling unit. Now the fan's driving the air through, the fan's driven by an electric motor. The chiller's a little bit like a refrigerator in some ways. If you go around to the back of your refrigerator, you'll find a coil on the back of that which is quite warm. Why is that quite warm? It's taking energy or heat out of the internal of the refrigerator, and it's actually pushing it out into the atmosphere with the coil on the back. So what I'm saying is the chiller, once it takes the heat out of the water, it needs to put that heat somewhere. And typically in a building, that heat is exported to a cooling tower, and we use evaporation to cool that water down. And then that water is cycled back to the chiller as such as a cooler temperature. So that's why you've got cooling towers in the building. They're effectively exporting the heat or the energy to the atmosphere using the evaporation, if you like. No different to putting a wet, sweaty arm out of the window when you're driving along in your car. Your arm feels cool. That's what evaporation does. It takes the heat away as such. So in all of this, you've got motors driving fans, motors driving pumps, motors driving machines around chillers, you've got motors driving fans. That's where the energy is being consumed. Of course, you've also, in these things here, got air being mixed. So hot air and cold air is being mixed to get just the temperature you want. That's another aspect, of course, that's just one room. If you think about a high-rise office tower and think about a floor plan and think about the heat loads. So the heat loads internally will change as people come and go during the day, but also as the sun moves around the building. So you've effectively got 5 zones in a square floor plan. You've got an internal zone where really there's not a great deal of effect from the sun. You've got a north zone, east zone, west zone, south zone. And these vary throughout the day. So you effectively have, in some sense, 5 rooms per floor as a minimal sense. Think about that in a 50-storey building. That's 250 rooms. That's a degree of complexity, I suppose, even before you start thinking about enclosed offices, or you start thinking about meeting rooms that need more outside air than, say, a one-person office because you've got 15 people in the room. So all of a sudden, whilst the basic principles aren't complex, once you start to multiply that out in terms of the spaces in a building and the differing requirements throughout the day, the thing becomes quite complex in terms of scale. So all this needs controlling, as you'd imagine. And what we find in buildings is we have things called building management systems, building automation systems, building management and control systems. They're effectively the brains and the nervous system of the building. And so you've got a myriad of sensors, a myriad of feedback loops, a lot of wiring, and obviously a computer head end which is controlling all these things as to when things work, how they work, and importantly how they work together. So it's not enough to simply control a boiler or control a chiller. You've actually got to control all those things so they actually work in concert. And that's really where we get to when we start talking about tuning. Control systems don't use energy. These things use energy, and control systems are effectively the methodology you use to tune those systems so that they actually work properly together. So there's no wasted effort as such. So what do these things look like? The imaginatively named air handling unit looks pretty much like you'd expect, just a great big insulated box with doors on it. Cooling towers, I'm sure you've seen them on top of buildings and outside car parks and things like that, are pretty much, again, a box. You've got airflow, you've got water flowing down through the box, air flowing up through the box. And when the water meets the air on a surface, you've effectively got an evaporative effect which cools the water. Chillers we talked about, large refrigeration plant, refrigeration compressors, controls, heat exchangers and what have you. In some ways, pretty much the same device that sits in the bottom of your fridge on a larger scale. And boilers, again, burner, large heat exchange area, a vessel full of water effectively which is being exposed to the heat. These are the sorts of things you see in basements and plant rooms.